A coastline is the planet's handwriting. It is the thin, restless line where solid ground meets moving water, and it never stays still for long. Storms can redraw it in a single night. Tides pull it like a breathing lung, twice a day. Glaciers can carve it with the patience of centuries, then vanish and leave the sea to rush in. Volcanoes can add new land in hours, and waves can erase that same land with a slow, relentless grind. If you want to understand how Earth works, stop looking at the middle of continents. Watch the edges. The strangest coastlines in the world are not random scenery. They are evidence. Each one is a record of forces you cannot see directly, but you can read them in cliffs, in curves, in islands scattered like debris, in bays that flood and drain like giant machines. Stay with the shoreline long enough, and it starts telling you what shaped it. Along Norway's western edge, the sea does something that feels almost unfair. It doesn't just touch the land, it invades it, sending long, narrow waterways deep inland between steep walls that rise like dark ramps. These are fjords, and they are not simply flooded valleys. They are valleys cut far below today's sea level by glaciers during the ice ages, when thick rivers of ice flowed downhill under their own weight. As a glacier moves, it scrapes bedrock with embedded stones and grinds it down. And because ice can be hundreds to over 1,000 meters thick, it can carve astonishingly deep troughs. Some Norwegian fjords drop more than 1,000 meters below the surface, with cliffs that make the shoreline feel like a mountain range that forgot to end at the water. The weird part is what happens after the ice melts. The ocean pours in and fills the over-deepened channel, but the glacier often leaves behind a threshold of rock and sediment near the mouth, called a sill. That sill can make the inner fjord deeper than the open sea outside it, changing how water circulates and how oxygen moves through the depths. If you've ever wondered how a coastline can act like a sealed container without a lid, fjords are the answer. The coast isn't just a boundary here, it is a carved passageway with a history of ice pressure, rock fracture, and a sea that arrived late to the scene. Across the Atlantic, a very different kind of coastline looks like it was built from tiny pieces scattered across the water. Along parts of Scotland, Ireland, and the Arctic shores of Canada and Alaska, you find shores crowded with skerries and small islands, uneven rock knobs, and narrow channels that twist like a maze. This is what happens when glaciers don't cut one clean trench, but instead bulldoze and polish a whole landscape of fractured bedrock. Ice sheets crush into the ground, pluck blocks from weak zones, and smooth the hard ridges. When the ice retreats and sea level rises, the ocean floods the low spots and leaves the highs sticking out as islands. The coastline becomes a topographic map in 3D, a drowned and fragmented terrain where the sea occupies every weakness. If you watch this kind of coast from above, it rarely forms a neat line. It looks shredded. That shredding matters because it creates enormous surface area. More coves mean more sheltered water, more habitats, more places where boats can hide from open ocean swells. It also means navigation is harder and local currents get complicated fast. A jagged coast is not just dramatic, it is a physics problem. Now shift south to Croatia's Dalmatian coast, where the pattern becomes even stranger. Long, narrow islands that run parallel to the mainland like a barcode. This Dalmatian style of coastline is famous enough that geographers use the name as a category. The mechanism is simple, but the result looks designed. Imagine a landscape of ridges and valleys aligned in one direction, often produced by folded rock layers or long fault-controlled terrain. When sea level rises and floods the valleys, the ridges remain above water as islands. And because everything is aligned, the islands line up with the coast instead of cutting across it. The shoreline turns into a series of channels, protected waters, and narrow passages that stretch for kilometers. It is not an island chain created by volcanoes or coral. It is a drowned skeleton of the land structure. On the other side of the world, Vietnam's Ha Long Bay feels almost like the opposite. Thousands of steep limestone towers rise straight out of the water, with narrow channels between them and caves hidden inside. It doesn't look like ridges and valleys. It looks like the sea is filled with stone teeth. This is karst, and the key ingredient is limestone, a rock that dissolves in slightly acidic water. Rain picks up carbon dioxide from the air and soil, becomes weak carbonic acid, and slowly eats the rock along fractures. Over long spans of time, that chemical weathering can carve caves, widen cracks, and isolate pillars. When sea level rises and floods a karst landscape, You do not get gentle hills turning into islands. You get steep towers because the rock has been dissolved into sharp relief. What makes this coastline feel almost unreal is that water shaped it twice in two different ways. Fresh water did much of the dissolving when the landscape was above sea level. Then the ocean arrived and turned the sculpted hills into islands. Caves that formed in air can end up partly underwater, and tides can pulse through them. The coast becomes a hybrid of chemistry and sea motion, and the geometry is the proof. A coastline can also be built by the sea itself, grain by grain, and that is where you start seeing shapes that look like engineering. Along the U.S. East Coast, especially from New Jersey down through the Carolinas, long barrier islands run like thin shields between the Atlantic and the mainland. The Outer Banks are the most famous example, and they are not fixed land in the way mountains are land. They are moving sand. Waves approach the shore at an angle, pushing sand along the beach in a process called longshore drift. Storms pile sand over the islands, and inlets open and close as hurricanes and nor'easters punch through. Over decades, barrier islands can migrate landward because storms carry sand from the ocean side and dump it on the bayside. If you want a number that makes it real, consider that major storms can shift entire dunes and cut new inlets overnight. Over longer periods, the islands can move meters to tens of meters per year in places, depending on sediment supply and sea level trends. That is why you see roads rerouted, houses moved, and dunes rebuilt. A barrier island coastline is a living conveyor belt. It exists because of constant rearrangement, not despite it. Up in Massachusetts, Cape Cod curls like a hooked arm reaching into the Atlantic. That shape is not random. It is a deposit left behind by glaciers and then heavily reworked by waves. During the last ice age, the Laurentide ice sheet reached into what is now New England. It dumped huge piles of sand and gravel at its edges. When the ice melted, sea level rose and waves began to reshape those deposits, carrying sediment along the coast and building spits and hooks. The Cape's curve tells you about prevailing wave directions and where sediment could travel. It is a coastline written by transport. Not carving, not dissolving, but moving. If you have ever walked a beach and seen the sand change from coarse to fine as you move along it, you're watching that process in miniature. Scale it up to a coastline and give it thousands of years, and you get peninsulas that curve, islands that slide, and bays that fill in. The shoreline becomes a slow-motion river of sediment. Some coasts are strange because the sea rises and falls so dramatically that the shoreline itself feels like a machine cycle. The Bay of Fundy in Canada is the classic. In parts of the bay, the difference between low and high tide can reach around 16 meters, more than a 5-story building. That is not because the moon is stronger there. It is because the shape of the bay and the timing of the tides line up in a way that amplifies the water's motion. Fundy is long and narrowing, and its natural sloshing period matches the rhythm of incoming tides closely enough to create resonance. Water is pushed in and out with extra force, and the coastline experiences extreme exposure twice a day. Where this gets truly strange is in the mudflats and tidal rivers. At low tide, vast areas become land you can walk across. At high tide, those same flats vanish under fast-moving water. Erosion and deposition happen on a schedule you can set your watch to. If you want to understand why some coastal communities build around tides the way inland towns build around seasons, this is the place. The shoreline isn't a line on a map here. It is a moving front with predictable power. Resonant tides also create tidal bores in certain rivers, where a wall or a surge of water travels upstream as the tide rushes in. It is not a tsunami. It is the ocean pushing into a narrowing river channel so quickly that the flow forms a wavefront. The conditions have to be right: a big tidal range, a shallow river mouth, and a shape that funnels incoming water. When it happens, the coastline's influence extends inland, and the boundary between sea and river becomes a traveling event. Not all coastlines are shaped mostly by water. Some are shaped by the land rising or falling. Along parts of Alaska and Chile, the Pacific Rim is actively changing because of plate tectonics. These are subduction zones where one tectonic plate dives beneath another. Stress builds for decades or centuries, and then releases in major earthquakes that can suddenly lift a shoreline upward or drop it downward. A few meters of vertical change does not sound dramatic until you realize it instantly shifts where waves strike, where tide pools sit, and whether harbors become too shallow or suddenly deeper. After large earthquakes, you can sometimes see ghost shorelines, old barnacle lines left high and dry on uplifted rocks, or drowned forests where the land subsided and seawater killed trees that used to stand above the tide line. Volcanoes add another kind of weirdness because they can create coastlines that are young enough to still be hot under the surface. In Hawaii, lava can flow into the ocean and build new land called lava deltas. It happens when molten rock pours over a cliff into seawater, cools rapidly, and piles up as rubble and new crust. The process is violent. Water flashes into steam, fragments rock, and creates unstable piles that can collapse without warning. The coastline expands, then sometimes falls away. It is land under construction with no safety rails. Iceland shows this on a larger scale. Sitting on the mid-Atlantic ridge, it is a place where magma rises as plates pull apart. Its coastline includes black sand beaches made from basalt, a volcanic rock that breaks down into dark grains. Add the North Atlantic's energy and frequent storms, and you get shorelines where waves hit with enough force to rearrange entire beaches seasonally. Sea stacks and basalt columns along some coasts form when lava cools and contracts, cracking into geometric shapes. Then the sea exploits those fractures and removes blocks. The rock looks precise, but the mechanism is straightforward. Cooling physics plus wave erosion, repeated for thousands of storms. Speaking of wave erosion, few coastlines show it as cleanly as places with tall sea cliffs and isolated pillars. Along parts of Australia's southern coast, limestone cliffs and formations like the 12 Apostles exist because waves attack weaknesses in the rock. First, sea caves form where the cliff is fractured, then arches open as caves connect or widen. Eventually, the arch roof collapses, leaving a sea stack. Given enough time, the stack collapses too, leaving a stub that disappears below the surface. The coastline is not static architecture. It is a sequence. If you visit twice in a lifetime, you might see a different lineup because collapse is part of the design. The Pacific Northwest in the United States has its own version, with rugged headlands and stacks along Oregon's coast. What makes it particularly dramatic is the wave energy. The North Pacific can generate long-period swells that travel thousands of kilometers, delivering force to the shore even on sunny days. Add winter storms and you get erosion that is not constant but episodic. A coastline can look unchanged for years, then lose a section of cliff in one night. Some coasts look strange because they were never carved or built by waves in the first place. They were drowned. Consider the Chesapeake Bay in the United States, which is essentially a drowned river valley, or RIA. When sea level rose after the last ice age, ocean water flooded up river channels, turning them into long estuaries. RIAs have branching shapes because rivers have branching tributaries, so the coastline becomes a tree-like network of inlets. That network matters. It creates sheltered waters, mixing zones where fresh and salt water meet, and habitats like marshes that trap sediment and nutrients. Europe has famous RIAs too, like along the coast of Galicia in Spain. The pattern is a reminder that sea level change does not just move the shoreline inland evenly, it invades existing drainage systems. The coast you see today can be an old river system with saltwater in it. If you live near one, you are living inside a flooded map of the past. In contrast, there are coasts that rise out of the ocean rather than being invaded by it. Coral reefs can build coastlines that look like rings, walls, or chains of tiny islands. The Great Barrier Reef is the largest system on Earth, stretching over 2,000 kilometers along Australia's northeast margin. It is not a single reef, but thousands of reefs and hundreds of islands, built by coral polyps that secrete calcium carbonate skeletons. The mechanism is biological, but the geometry is geological scale. Coral growth is slow on a human clock, often measured in millimeters to centimeters per year, depending on species and conditions. Yet given thousands of years, it can build structures that redirect waves, create lagoons, and protect shorelines behind them. Barrier reefs form where reef growth keeps pace with sea level changes, building upward as water rises. If you want to appreciate the engineering, look at the wave environment. The reef crest breaks incoming waves, converting a violent swell into calmer lagoon water. That changes erosion patterns on the coast behind it, and it can allow sand islands to exist where they otherwise would not. Atolls take that story further and make it stranger. An atoll is a ring-shaped reef with a lagoon in the center, often with low islands on the rim. The classic explanation traces back to Charles Darwin's idea of subsidence. A volcanic island forms, coral grows around it as a fringing reef, then the island slowly sinks or the sea rises. Eventually, the volcanic core drops below sea level, leaving only the reef ring. The result looks like a deliberate circle drawn on the ocean, but it is a time-layered process of volcanic construction, followed by slow sinking and persistent biological building. You can test your own intuition here. Ask yourself what would happen if the coral could not grow fast enough. The reef would drown and disappear below the surface. The existence of an atoll tells you that, at least for long enough, coral growth and water level change stayed in a workable balance. That balance is the hidden mechanism behind the shape. Then there are coastlines shaped by ice not just in the past, but right now, where the boundary between land and sea is tied to freezing and thawing. In parts of Antarctica and Greenland, the coast is often an ice front. Glaciers flow into the sea and become floating ice shelves, and those shelves can calve icebergs that break off like slow-motion explosions. Calving events can release ice blocks the size of small cities, and when that happens, the coastline shifts without the sea ever touching bedrock. Even outside the polar extremes, seasonal sea ice changes what waves can do. Ice can dampen wave energy, acting like a temporary shield. When it is absent, storms hit coasts directly and erosion can accelerate. In the Arctic, where warming trends have reduced seasonal ice cover in recent decades, some coastlines are eroding rapidly because permafrost cliffs melt and collapse into the sea. The odd part is that the rock in these cliffs is often frozen sediment, held together by ice. When it warms, the coast can fail like thawing concrete. If you want a coastline that looks like it was cut with a knife, look at places where rock layers stand nearly vertical and the sea uses that structure like a template. On parts of the Na Pali coast of Kauai, Hawaii, tall ridges and narrow valleys create fluted cliffs. The mechanism includes volcanic construction, but erosion is the sculptor. Heavy rainfall feeds streams that cut into the rock, while landslides peel off sections of cliff. Because the rock layers and fractures guide where failure happens, the coastline develops repeated grooves and spires. It is not one process. It is rainfall, gravity, and rock strength arguing continuously. In places like New Zealand's fjordland, you see a collision of mechanisms. Glaciers carved deep valleys, then sea level rose, then ongoing tectonic uplift and heavy rainfall kept steepening slopes and triggering landslides. That combination creates coastlines where the sea meets mountains almost immediately with little coastal plain. When land rises and rivers cut down to keep up, slopes remain steep. The shoreline becomes a cliff edge rather than a beach. Different forces can produce similar drama, but the details tell you which ones were in charge. There is also a category of coastline that exists because a river and the sea are constantly negotiating territory. Deltas are the obvious example. The Mississippi River Delta is a machine that delivers sediment to the Gulf of Mexico, building land outward. But the sea fights back with waves, storms, and subsidence. River deltas often form a bird-foot shape when sediment is pushed straight out in channels, as in the Mississippi, because wave energy is not strong enough to smooth it into a simple arc. Change the balance and you get different shapes. Where waves dominate, coastlines become smoother, and sediment is spread along shore. Where tides dominate, channels can become more complex with sandbars and tidal flats. A coastline built by a river needs constant supply. Cut that supply and the sea begins reclaiming the delta. That is not philosophy, it is sediment accounting. One of the strangest patterns you can see from space is a coastline that looks like a string of beads, with repeating bays separated by headlands. In some places, that comes from alternating rock types. Hard rock resists erosion and becomes headlands. Soft rock erodes faster and becomes bays. Over time, waves refract around headlands and focus energy into certain spots, deepening the bays further. The coast organizes itself into a pattern because erosion is not uniform. It is guided by rock strength and wave physics. You can see this principle on parts of California's coast where cliffs and coves alternate. California adds another twist: active faults and rapid uplift in places. In areas where land is rising, old wave-cut platforms can be lifted above sea level, forming marine terraces. These terraces are flat benches cut by waves during past sea level stands, then raised like stairs. Walk along a terrace and you are walking on a former shoreline, now stranded above the ocean. The coastline is recording not only wave action, but vertical movement of the land. Some coastlines become strange because they are made of materials that do not behave like solid rock. Consider coasts built from unconsolidated glacial till, soft sediment, or clay. They can slump, slide, and collapse under wave attack. The cliffs along parts of England's Holderness coast are famous for rapid erosion because the material is weak and the North Sea delivers persistent wave energy. When the base of a soft cliff is undercut, the upper part collapses and the cycle repeats. You do not need extraordinary storms to change a coastline like this. By now you can feel the pattern. The strangest coastlines are not defined by one cause. They are defined by which causes one and for how long. Ice can carve, then the sea can flood. Tectonics can lift, then waves can cut. Chemistry can dissolve, then tides can pulse through the result. Living organisms can build a reef, then storms can pile sand into islands behind it. So here is a question to keep in the back of your mind as you look at any shoreline, whether it is a quiet lake edge or the open Pacific. What is this coast made of, and what is the strongest force that regularly hits it? That answer is usually the real shape: rock type, wave energy, ice history, sea level, and plate motion. Those are the sculptors, and they leave signatures you can learn to read. The next time you see a beach, do not treat it like a backdrop. Watch the angle of the waves, look for layers in the cliffs. Notice whether the shoreline is straight, hooked, shattered into islands, or sliced into deep bays. That geometry is not decoration. It is a record of energy, time, and material. Coastlines feel familiar because humans build near them, vacation on them, and photograph them constantly. Yet the world's strangest shores prove the edge of land is one of the most active places on Earth, shaped by forces that can be gentle for 1,000 days and then decisive in a single night. If you know what to look for, every headland and inlet becomes an explanation you can follow. Subscribe and be curious.